All right, guys, we're going to do one more lesson on the limit definition of a derivative. This is lesson 4. And it's just a question that you may see on the AP exam. I've seen them ask this type of question many times, actually. Let's go ahead and jump in and take a look at it. We've learned 2 limit definitions of derivatives. So we have this one here, which is the classic one, and then we have this one here, which is the alternative form. Now, I'm going to start off with the alternative form today because it's a little bit easier to understand, and it kind of might help you grasp the idea a little bit better of what we're going to be doing before we get to the regular looking one. So, in order to do the problems that we're doing today, basically, what you're going to need to do is recognize that when you're looking at these, I want you guys to recognize you're not looking at just any old limit. Okay, you're looking at an actual derivative. So, I know that you guys, whenever you look at, actually, undo that. When you guys look at this, you know that we're talking about derivatives, right? But I want your guys' minds to be trained in such a way that when you see something that looks like this, you also know you're looking at a derivative, because this is the limit definition of a derivative. They're literally the same thing. And so that's kind of what today's lesson is all about. So today's lesson is going to be where I'm going to present you with something that looks like this. And you need to identify a couple of things. What is the function? And what value am I finding the limit of this function at? And finally, we could even find the answer. All right? But let's identify a couple of things. So I would write down the slide, and what I would do is I would circle this, and I would say, okay, well, if you're looking at the alternative form of the limit definition of a derivative, whatever's right there represents your function. Right? And over here, I'm finding the derivative at c, right? Well, that means that whatever number's right here, that's our input value. That's the value that we're finding the derivative at. Okay? So we're basically going to need to recognize that this, in fact, is a derivative. And you could tell because of the way it looks, right? You have your y2 minus y1 over x2 minus x1. So you want to recognize that that is the limit definition of a derivative. And then from that, after you've recognized it as being one of those types of limits, you should be able to tell me what the function is and what value they're finding the derivative at. And then that's pretty much what our lesson is. It's kind of a weird thing, but that's how we're doing it. So let's go ahead and take a look at an example. So go ahead and write down example 1 here. Now, as you guys are looking at this, I want you guys to recognize that, we are in fact looking at the limit definition of a derivative. Why? Because I have something minus something over something minus something, right? That sure looks like a y2 minus y1 over x2 minus x1. And when you just apply a limit to that, that's what we call a limit definition of a derivative. So this has the alternative form of a limit definition of a derivative. Okay? So this is not just any old limit we're looking at. This is a very special limit that gives us a derivative. Okay, so now the next question is, the derivative of what? What function are we finding the derivative of here? Well, as I told you, the function is right here. It's that first part. Remember, it's f of x minus f of c. This represents f of c, but we don't really care about that at the moment. We care about this. This is my f of x. So the answer is we're finding the derivative of this function, which I'm going to call f of x, and that function is e to the 3x plus 1. Okay, so this limit here is not any old limit. That's a limit that represents a derivative. And it represents the derivative of what function? Of this function. But we're going to go take it another step now. whenever we have these, it's not just representing the derivative, but it's representing the derivative at a specific point. So, at what value of x are we finding the derivative? At what value of x are we finding the derivative? Well, that is the value we're finding the derivative at. So it's at x equals 1. Okay? And so what function are we finding? What function does this limit represent the derivative of? It represents the derivative of this function at this point. Okay? And then finally, this last step is kind of a little bit less important than the first two steps. I really want you guys to be able to identify, okay, this is not any old limit, this is actually a derivative. And then I want you guys to identify, okay, it's the derivative of what function and at what value. That's the most important thing I want you guys to get out of this. But the rest of it, we can actually find the answer now. So step 3, we could say evaluate the expression. Actually, I'll just say evaluate the limit, which means find the limit. So now, not only have I gone through the trouble now of finding out what the function is and at what value I'm finding the derivative, but we can actually just find the limit now. Okay? This part is not as important because it's pretty much review from beginning to end. Now, I just want to show you guys 2 ways to do it. Okay? So here's method 1. Method 1 is to apply L'Hopital's rule. Okay, and I'll show you how it works. So by direct substitution, you would get 0 over 0. And you guys can test that if you want. Okay, but if you plug in 1 here, you're going to get e to the 4th minus e to the 4th over 1 minus 1. So you end up with 0 over 0. So this is a L'Hopital limit. Okay, and therefore we're going to apply L'Hopital's rule. So, according to L'Hopital's rule, I guess I'll write that out by L'Hopital, we could say that the limit as x approaches 1 of e to the 3x plus 1 minus e to the 4 over x minus 1 is equal to the derivative of the top and bottom there. So, if I take the derivative of the top, the e to the 4 is just going to go away because that's a constant. This one we're going to apply the chain rule to it. So first of all, when you take the limit of an e function, you always just get that e function all over again. But we also need to multiply it by the derivative of its inside, which is the exponent in this case. So the derivative of 3x plus 1 is 3, so I'm going to put a 3 in the front. And the derivative of the bottom is 1. And then we could just go ahead and plug in our 1. And what we end up with as a result is we end up with 3e to the 4th power by direct substitution, and we're done. So that's method 1, just doing what we did in unit 3. You know, we try direct substitution first, we get an indeterminate form, so by L'Hopital's rule, we can get the answer that way. But here's method 2. And now method 2, you're probably not even going to see much of a difference, honestly, between method 1 and 2, but they are a little bit different. Okay, so method 2 is going to be capitalizing on what we've learned today. Okay? All right, so I would say since this limit, and by the way, this little sentence I'm writing out, I wouldn't expect you guys to write this out on your homework or on a test or anything. I'm just doing this for teaching reasons, and I think you guys should have it in your notes as well. But in general, if you're doing an exercise, you don't have to write out this sentence. But for notes, I would encourage you to write it. So since this limit represents the derivative of the function e to the 3x plus 1 at x equals 1, we can just use our shortcut that we learned in Unit 1. So how does that work? Well, here's my function. My function is e to the 3x plus 1. Now plus 1 is actually up in the exponent. The next thing I'm going to do is I'm going to take the derivative of this function, which is, once again, when you take the derivative of an e function, you just get the e function all over again, and you multiply it by the derivative of the inside, which is 3, and that looks familiar, doesn't it? And then if you want to find f prime of 1, all you do is you plug in 1, and you'll get your answer. So there's two ways to do this thing. One way is just to pretend like we're back in Unit 3. Oh, this is just a simple limit, so let's try direct substitution. Oh, it's L'Hopital's, so let's apply L'Hopital's rule. We'll get our answer. But method 2 is what we're going to be focusing on today. Method 2 is the one I'm going to do for the rest of these today, but you can always do the other one. But method 2 is recognizing what's the function and at what value am I finding the limit. Cool. So let's just apply the shortcut for derivatives, because this is not just any old limit, this is a derivative. Okay? So that's pretty much it. So a lot of times what they'll do is they'll give you problems on the AP exam where it'd be really kind of difficult to try to evaluate the answer using the old school method over here. And so it's a little bit more beneficial to recognize what the function is and at what value you're finding that limit, and just recognizing in general that it does represent a derivative. So that's pretty much it. Kind of a weird type of lesson today, but just want you guys to kind of get used to those types of questions. Let's do another one here. From now on, I'm not going to do both methods. I'm just going to stick with the third method, but you could always do method 1 if you wanted to. All right, so here we go. First of all, what function does this represent? Okay, well, it was this. That first part right there. Now, you guys might notice there's a little bit of a problem here with this one, though. I don't know if you guys are noticing this, but notice that there's a plus here instead of a minus. Isn't it supposed to be y2 minus y1 over x2 minus x1? Well, it actually is still correct. If you were to plug in 0 here, you're going to end up with negative 40 for this squared part. 0 minus 2 is negative 2. Negative 2 cubed is negative 8. And negative 8 times 5 is negative 40. So what we have here is our function minus a negative 40, so it becomes plus. Something else is wrong on the bottom here. It's supposed to be x2 minus x1, right? But I only see one thing down there. Well, it's always being subtracted by the c, and in this case my c is 0, so why have it there? So really, if you wanted to rewrite this a little bit, you could, so it looks a little bit more like the limit form of a derivative. I'm sorry, that's supposed to be a 0. So you could rewrite it like that if you wanted to. And now it looks more like the limit definition of a derivative, right? And so now we can see that my f of x is this, my f of c is this, here's my x, and here's my c, and here's my c. So the function I'm finding the derivative of is this guy right here. So at what value are we finding the derivative? That would be this number here, so 0. And then finally for step 3, we want to use our shortcut to evaluate the limit. We want to use the derivative shortcuts to actually evaluate our limit. So I'm going to show my work up here. So we start off by identifying the function. Next, we find the derivative of that function because this limit represents a derivative. So we do the power times the front, and then we subtract 1 from the power, times the derivative of the inside, which is just 1. And then we plug in the x value that they give us. And then from there we just simplify using order of operations, of course. So this is going to be negative 2 to the second power. Negative 2 to the second power is 4. So I've got, this is times, not minus. So negative 2 to the second power is 4. And 15 times 4 times 1 would be, what would that be? It would be 60. So there's our answer, okay? Once again, you could have just did L'Hopital, do your direct substitution and apply L'Hopital's rule to it. But the point of today's lesson is I want you guys to recognize, oh, this isn't just any old limit. That's a derivative. What's the function? At what point? Well, let's just use the shortcut for derivatives to find the answer. All right, let's do another one. It's kind of an obscure topic, so I just want to do a couple of examples just to really make sure that it's sinking in for you guys. So I'm looking at this and I recognize, this looks an awful lot like an f of x minus f of c over x minus c. We have a little problem there. It's a plus, but that can happen if sometimes your f of c is a negative number, because if you subtract a negative, you get a positive. So this sure looks like the limit definition of a derivative to me. And so what function is it the derivative of? Well, it looks like we're finding the derivative of sine of 2x. And at what value are we finding the derivative? Well, that would be the number that's right there. And for step 3, we want to evaluate the limit. Now, once again, you could do L'Hopital on this and probably get the right answer. But what we're going to do is we're going to do it the derivative way. So since this limit represents the derivative of this function, I'm going to start by finding the derivative of that function using my shortcuts. It's a chain rule. The derivative of the outside is cosine. The derivative of the inside is 2. And then I'm going to plug in the number that they give me to plug in, which is pi over 8. Okay? Two times pi over 8 is pi over 4. Cosine of pi over 4 is radical 2 over 2. And 2 times radical 2 over 2 is just radical 2. There you go. So this limit up here represents a derivative. It represents the derivative of this function at this point, and so I just used our shortcuts from Unit 1 to find out what the answer to this limit would be. Okay, let's do one more problem here. So, once again, on number 4 here, we're not looking at just any old limit. I see an f of x minus f of c over x minus c pattern here. So this represents a limit definition of a derivative. And this represents the derivative of what function? This piece right here. So it's the cube root of 3x plus 2. And at what value are we finding the derivative? At x equals 2. And then finally, we're going to evaluate this using our shortcut methods, okay? So here we go. Once again, I'm going to show my work over here, so I'll need a little bit more room. So since this limit represents the derivative of this function, I'm going to use my shortcuts to find the derivative of this function at this value. So the first thing we need to do is, first of all, before I even find the derivative from Unit 1, what we learned is that from Unit 1, we don't like our derivatives written as radicals. We like to have them written as powers first. Okay. The next thing I'm going to do is now I'm going to find the derivative using the shortcut. That's where you take the power and you multiply it to the front. And then you subtract 1 from the power. So there's my derivative. And now I'm going to plug in 2. Oops. And then we just go ahead and simplify it. So this is going to be 6 plus 2, which is 8. So I've got 8 to the negative 2/3 power. All right. So we need to know how to simplify that. So first of all, we're going to put that 8 in the denominator as a positive power there, right? Because we remember from Unit 1, negative powers move your terms to the denominator. The next thing we're going to recognize is that 8 to the 2/3 power means we're looking for the cube root of 8, and we're going to square it. Now the cube root of 8 is 2, and 2 squared is 4. So I have 1 over 3 times 4, which is 1/12. Ran out of space there, but there we have it. So the answer would be 1/12. All right? So, like I said, step 3 is not really my goal for you guys today, so much as recognizing that this represents a derivative, what the function is and at what value, but we still want to practice those Unit 1 derivative tricks to kind of bring it home. I've seen the question asked a lot on the AP exam where they'll say, this limit is equivalent to which of the following? And it'll just give you a whole bunch of different expressions. It could give you this, it could give you this or this. So the point is that if you can work your way up to that, then you're demonstrating that you know that that represents a derivative and of a specific function. All right, so let me bring up 2 problems for you guys here. I want you guys to go ahead and pause the video and see if you could do these 2 problems in the same way that I was doing them. First of all, I want you to identify what's the function. I want you to determine at what value are we finding the derivative. And then finally, I want you to use the shortcut to evaluate the answer. Okay, same 3 steps over here. So go ahead and pause the video. When you're all done, you'll see the solutions. Okay, so for number 5, the function that this limit represents the derivative of is tangent of x. We are finding the derivative at the value of pi over x. So we have those 2 facts from here. And that's the most important part. The next part is where, okay, so since this represents the derivative of this function at pi over 4, then basically we just need to find the derivative of tangent, which is secant squared, plug in our pi over 4, and get our answer, which is 2. Okay? Let's go ahead and take a look at number 6. The function we're finding the derivative of here is that, at the value of -1. And then here is the shortcut process for arriving at the answer, which would be 6 as a final answer. All right? Now, that's one way the problem could be presented. The problem is presented to us in that form with the alternative form of the limit definition of a derivative. But as you guys know, we have the other form, which looks like this. Okay? Now this one's can be a little bit more confusing. The reason why is because it's a little bit trickier to find out what the function is on these ones. And the reason why is because they're not going to have an x in there. Okay? The x is going to be replaced with a number, and that number is going to represent the value at which you're finding the derivative. So here's what I want you guys to do. I would encourage you guys to use colored pencils here. It might help a little bit. They're going to have a number right here. It won't be an x, it'll be a number. Okay? That number, whatever's right there, will represent our input. When you're doing the regular limit definition of a derivative, this will always be 0. Remember that represented like our delta x? That's not the input value, okay? So it's different than the alternative form. Whenever you're looking at the standard limit definition of a derivative, the input is the x value, which is there. Now technically it's here also, but the problem is that they're going to have already plugged it into the function and worked it out, and so you're going to see just a big number here that's something else completely. That's your y2 value, but we don't need that for the problem. So the number we're looking for is going to be located right there. Okay, so that's going to represent our input value. The function also will be a little bit tricky to identify because, like I said, they're not going to actually have a function here. They're going to have plugged a number in and then simplified it, and all you're going to see is some kind of a number right here. All right, and so that's not going to tell us what our function is, unfortunately. The way we're going to identify our function is by looking at what I'm tracing in red here. Okay? Actually, I take that back, not the h, but that'll be our function right there. We're going to ignore the h, and then whatever number they have right here, we're just going to ignore that and put an x there, and whatever's left is going to represent our function. So it's a little bit trickier to identify it because with this particular limit definition of a derivative, everything kind of gets jumbled up, and so we have to be a little bit trickier in how we pull out the information to identify what the function is and what the input is. So let's go ahead and take a look at some examples that have that for us. All right, so just look at it here for a second with me. One thing about these ones is the h is always approaching 0. You won't have a different number there. Now you don't have to write this if you don't want to. I'm just writing this for teaching purposes, but there's all that stuff. So the input, as I told you guys, will be whatever number is right here. Now in this case, in other words, what number are you adding to the h? Well, in this case, that would be the minus or the negative 1/2. So my input is a half. So we haven't figured out our function yet, so I'll wait on that. At what value are we finding the derivative here? Well, I'm sorry, at what function are we finding the derivative? We don't know the function yet. We will in a second. But what value are we finding the derivative at? Well, that would be the value x equals negative 1/2. So that's what this is, okay? Now, how do we find our function? All right, well, that's an interesting one. So let's take a look at it. So first of all, I'm going to take this expression here, and I'm going to do two things to it to find my function. First of all, I'm going to get rid of the h, and I'm going to replace this with an x. And that leaves me with x to the 4th. That's my function. So you do two things to this piece. You get rid of the h, and you change the number to an x. And then you've got your function. All right? So now I know that this limit here represents the derivative of this function at this value. All right? So let's go ahead and apply our shortcut to evaluate the limit. And once again, L'Hopital will work on these, but we're going to use the shortcut instead. Since we know this limit represents a derivative, we're just going to use the shortcuts from unit 1 to find the derivative. So here's my function. My function we've determined is x to the 4th power. the derivative of x to the fourth power is 4x cubed, and the value at which we're finding the derivative is a negative half. All right, so negative half to the third power is negative 1/8, and negative 1/8 times 4 is negative 1/2. And there we go. All right, so there it is. The number that's right here represents your x. Then you take this entire expression, and then you cross off the h, you change the number to an x, and you've got your function, and then you can apply your shortcut just like we did last time. Let's do another one to see if we can get to sink in a little bit better. All right, so we're looking for three things. We want to do the function. We want to find the input, or the value, I should say. That's what I've been writing usually, right? And then we want to do our shortcut, which I'll do over here. So let's first of all look at this and say, oh, okay, this sure looks like the limit definition of a derivative, the classic form, not the alternative form. What value are we finding this limit at? Well, that would be whatever number is being added to the h. So that's 81. So we're finding the limit at, we're finding the derivative at x equals 81. Now, what's my function? Well, like I said, we're going to take this entire piece here that comes before the minus, and we're going to do two things to it. We're going to get rid of the h, and we're going to change this to an x. So what we're really looking at here is the fourth root of x as my function. So this limit here represents the derivative of this function at this value, and now I'm ready to apply my shortcut to actually evaluate the answer. So let's do that. There's my function. Before I take the derivative, I'm going to change that radical into a power. Then I'm going to apply the rule for derivatives, which is where you multiply the 1/4 to the front and subtract 1 from the power, which would give me negative 3/4. And then finally we plug in the 81. And as you guys know from our previous example we did earlier, when you have a negative exponent, that causes that term to be pushed into the denominator. So now I have this. And you may also recall that when you have a fraction power, that can be rewritten as a radical when you're trying to evaluate it. The fourth root of 81 is 3, and 3 to the third power is 27. So now I've got 1 over 4 times 27, which simplifies finally to be 80 plus 20 is 108. So final answer is 1 over 108. Okay? So that was example 3. And so I'm just going to do two more examples a little bit more quickly just to kind of get the process streamlined, and then we'll let you guys practice here. So once again, here I'm looking at a standard limit definition of a derivative, and the value at which we're finding that derivative is this number. The function will be this whole piece here, where I take away the h and I replace this with an x. And so the function is f of x equals tangent of x. Shortcut time. Let's find that limit using derivatives because that limit represents a derivative. Here's my function. Here's the derivative. And then we're going to plug in the value they gave us. secant of 2 pi over 3 is 2. And it's being squared, so my final answer will be 4. All right. Here's number 10. Let's do another one. This will be my last example I give before I let you guys practice. So, what's the value? 4. What's the function? Drop the h, replace the 4 with an x. It would be ln of x. Shortcut. My function is ln of x. The derivative of ln of x is 1 over x. And if I were to plug in 4, I would have 1/4 as my final answer. Okay? So, let you guys try a couple of those. There you go. Go ahead and pause the video and see if you guys can identify the function, the value, and then actually evaluate the limit using derivative shortcuts. All right, guys, so there is our answers for those two, and that will end our lesson for the day. And so whenever you guys begin to do your homework tonight, you're going to have different ones. The ones that have h's are the ones that are the regular limit, and the ones that have just functions like regular equations here, the d, you can think of that as an x. Those ones are the alternative form of the derivative there. So just a few different problems, but anyway, good luck, and we'll see you guys in class.